what?
If you're going from flat space to curved space, keeping the same field, what does it mean to keep the same field?
Do we have to transform the field
all right,
to
let
a
me
curved field too?
let me try to. First of all, this is stuff that I would say is. You can sit down.
Yeah, I
want a candy.
No, it's
Here.
okay. I had one. By the way, I have to leave at 6 o'clock today, so
Okay.
somebody will have to, in a half an hour, somebody will have
Okay.
to take over the camera for me.
All right. So, the way I've been thinking about it is, what do we mean by a field? What we mean by a field is something that is a function of space and time, and that satisfies the appropriate commutation relations. That is to say, if you're in flat space, and if we're just talking about scalar fields for simplicity, and get this shit out of the way, what you're saying is phi of x and t, pi of y and t is I delta cubed of x minus y, where x and y are 3 vectors. This is in flat space-time. And pi, for a scalar field, is typically the partial derivative of the action density with respect to the time derivative of the field. Okay? All right. So, I'm carrying over that point of view to say what the field is, and so we can talk about the field we can quantize the field in different ways as long as it satisfies these relations. Okay, so let's. I suppose that's not really a full answer to your question, but the fact is that quantization in curved space-time is puzzling.
It's very interesting, though. I mean,
It's interesting and it's puzzling. Let me recall that what we're doing here is if we use the discrete formulation, then we're summing the field we're writing the field as a sum of annihilation and creation operators with respect to functions that satisfy the covariant Klein-Gordon equation, which is the equation of motion for the field. And let me write down the action of the field. It's minus a half integral square root of g d4 x gik di phi dk phi. One can add another term. I'll add it briefly, but I'm going to set this to 0 pretty soon. So this is the action of the scalar field. G is the metric of space-time, so the invariant metric is gik dxi dxk. This is the thing that is the same in any coordinate system. So it's the same thing as g prime ik dx prime I dx prime k. Gik is the inverse of G with 2 lower indices, so that's delta IL. And what else here? R is the scalar curvature. So you can look in, I put the chapter on general relativity, I put it on the class webpage, the chapter from the second edition of my book. So the scalar curvature is the thing that, it's the simplest scalar that one can make from the metric. And in fact, the Einstein action is, I will write this as a constant alpha, because I don't remember exactly what the constant is. It's something like oh Christ, I don't remember
It's
what
like
it
A
is.
pi g or something like that, 1 over A pi g.
All right, let's go with that. 1 over 8 pi g. But I don't know whether it's plus or minus, and it's r squared of g d fourth x. So that's actually the Einstein action. And so let's see. And this Einstein action is the trace of the Ricci tensor. So in other words, again, apart from factors of 1/2, r is r, let us say, ik g ik, and rik in turn is a trace of the curvature tensor, which is a 4-index object. And I'm not going to, I suppose that I can say that rik is r, a, b, c, d, g, well, no, it's not. Oh, God. Let us say A, B, C, D, G, I, A, G, K, B. I'm relying on the fact that the curvature tensor has a great deal of symmetry and anti-symmetry, and it may be that one gets this, but I will put a big question mark here, and this is proportional to, and so forth. And so let me write proportional to there. In any event, R is a scalar curvature. This term you can put in, but in most formulations one sets C equal to 0, so one simplifies things by getting the scalar curvature out of there. The scalar field still interacts with gravity because of the square root of G and the GIK, and the fact that the total action is basically S phi plus SE plus the actions of any other fields that happen to be in the problem. Now, the equation of motion, once we set C equal to 0, is di of square root of G, G I J dj Fn of x, say, is equal to m squared square root of G Fn of x. So that's the equation that the mode functions in which we'll expand the field must satisfy. And the idea is that one can also express the field in terms of another set of mode functions, and all the mode functions has to satisfy the same equation. Now, there's a scalar product that one can define. In flat space, the scalar product looks like this. I integral d cubed x Fn star of x time derivative, maybe I'll write that as a t, Fm of x minus time derivative of Fn star of x Fm of x. And this time derivative, this metric satisfies certain properties, provide, at least if the fields are suitably normalized, one can have in fact, we'll assume that they go like this. Fn star is minus delta Nm, and Fm star is just 0. This is a special case of a more general metric, and the more general metric is FNFM, and it is I integral square root of G on the surface d cubed S, some normal vector, and then F star dA n m minus dA Fn star Fm. Okay, like that. And what we're going to be assuming is that there are complete sets of solutions to this equation, and they satisfy these.
Can I ask a quick question?
Yeah.
Yeah, so I don't know, maybe I'm thinking of this wrong, but these FNs, I'm thinking of like super simple case. We could think of them being like e to the ikx.
Yeah.
Right? Okay, well, in that case, Fm star, isn't that f of minus m?
Yeah.
Oh, well, I guess, yeah, sorry, well then I guess, yeah, they would indeed be, their inner product would indeed be 0 unless n and m were both equal to 0. So I guess, I'm just thinking of this last condition, this Fn, Fm star equals 0.
Right.
And I was thinking in the case of e to the ikx, do we get any exception? But that's, I guess, only if n and m are both equal to 0. Would this be non-zero?
Yeah.
But that's, I don't know, that's kind of a funny case, though.
Well,
Yeah.
we also have these time derivatives.
Yeah, it would be 0. Yeah,
And I think
nice,
the point
yeah.
is that the
It's a
time
constant.
derivatives,
Oh, yeah.
if they're going
Good point.
to cancel things down, you get let me just make sure I've got this written correctly. If n star in fact, I should have written this more generally as this inner product more generally. So let me do that. G. And then we get rid of this N. And then we make this G. So this is our scalar product. The scalar product is defined without regard to how we're labeling things. And then down here also, we want to just do this, and so we'll get rid of the N. This is what I actually put in my notes, but I unfortunately have been sometimes ignoring my notes when I write things like when I wrote this on the board. Now, this scalar product in particular is Hermitian. So Fg star is Gf. And it also satisfies the rule, and I don't know what to call this relation, but I'll write it down this way. So both of these definitions, the flat space and the more general curve space in a scalar product, satisfy both of these rules. And we're going to assume there's a complete set of solutions for a given metric and that they have these orthonormal. We can make the solutions orthonormal. And this S is some surface that's space-like, and one can show that a thing is independent of which surface you choose. And so the idea is to expand the field in terms of two different sets of annihilation and creation operators, and equivalently, two different sets of solutions to the field equations. And now this is extremely general, though. What we can say here is this is a scalar product, but we could say that we have we could abstract from this and consider a more general scalar product. And what we want is that the thing be Hermitian, that it satisfy this rule, and that we're able to get have orthonormality relations like that. So that's why the Bogoliubov transformations are used throughout physics. They're not restricted to special relativity or general relativity or cosmology. They're very, very general. And all right, so now I'm going to go through some algebra, and in particular, I'm actually going to follow the notes so as not to screw up. This FL, the scalar product of FL with the field, this is going to be a sum on n, A of n, FL with Fn, plus AN dagger, FL with Fn star. And now if we use the orthonormality, Fn with Fn star vanishes. Fn with Fn is delta n m, or Ln here. And so this is just A sub L. And similarly, if we do this on the primed, if we use a primed function, in other words, a mode function from a different complete set of solutions of the field equations, what we will have is sum on n, A sub n, FL prime, Fn plus A sub n dagger, FL prime, Fn star. And on the other hand, what I said I was going to follow the notes, but unfortunately I did not follow the notes. What we're going to do is we're going to expand phi in terms of the prime functions and the prime operators. So we put in the primes like that, and now we see this gives us AL prime. And the corresponding case for creation operators, or cases for creation operators, we would use FL star. This will give us a sum on n, AN, FL star, Fn plus AN dagger, FL star, Fn star. This one vanishes. This one gives us a minus sign. So this is minus AL dagger. And then similarly, F prime L star with phi. If we expand phi in terms of the primed operators, have and this last one gives us minus A prime L dagger. Because the product of two primes just gives us a minus sign. So this is how we can get creation annihilation operators from scalar products of solutions with the field. Now, since these mode functions are complete, we can use them to expand the other mode functions. And this is one of the key things of the Bogoliubov transformations. We'll do a sum over I, and the notation, I'm using Davies notation, alpha ji fi plus beta ji fi star. So this is a way of expressing the second set of solutions in terms of the first set of solutions and their complex conjugates. And we can then identify these coefficients by taking further scalar products, namely FL with F prime J is then a sum over I, AJI, FL with FI, plus beta JI, FL with FI star. This one is 0. That one is delta LI, and so this is alpha JL. Similarly, to get the betas, we'll take the inner product with FL star. And we get a sum on I, AJI, FL star with FI, plus beta JI, FL star with Fi star. And it's the last one that is non-zero, but it kicks out a minus sign, so we get minus beta J L. And that minus sign, you can compute that from either one of these formulas for the scalar product, or equivalently, you could just use this expression, namely that the scalar product of F star G star is minus the scalar product of FG, and that would give you the same answer. Now, to find the inverse relations, well, we'll just write Fj as a sum on I of gamma ji, F prime I, plus delta ji, F prime star I. So these are the inverse relations, and we can use this same technique to find the inverse coefficients, gamma and delta. And the way we do that is the same way we did this, namely that F prime L Fj is a sum on I, gamma ji, F prime L F prime I, plus delta ji, F prime L, F prime star I. And this one's 0. This one is delta Li, and so this is equal to gamma JL. Similarly, F prime star L Fj will be a sum on I gamma Ji F prime star L comma Fi prime plus delta Ji F prime star L F prime star I. And now the first term is 0, and the second time kicks out a -1. And so this is equal to minus delta JL. Okay, but now this scalar product is Hermitian, and it obeys these two rules. Who's manning? Obeys these two rules. This is hermiticity. Does anybody know what this is? Is there some meaning, some name for this? All right, I don't know what it's called. Well, let's look at gamma JL. Gamma JL is FL prime FJ, and so this is FJ, F prime L complex conjugate, but on the other hand, FJ and FF prime is an wait a second, where am I? Right. An FF prime is an alpha, and what we have here is an FF prime complex conjugate. And so this is an alpha complex conjugate, and the indices turn out to be LJ. And it's the opposite of the way they occur, so JL goes to LJ. The other term requires a little more work, namely delta. What we found was that delta JL was minus F prime L star FJ, and this is minus FJ FL prime star complex conjugate. That's the hermiticity character. You switch the order without changing the sign by doing a complex conjugation. On the other hand, the other property whose name I don't know means that you can bring the star inside at the cost of a minus sign. So this becomes F star J F prime L. Now we recognize this as an F star F prime. An F star F prime is a beta with a minus sign, and so this is minus beta something. The beta indices are also backwards, and so this should be LJ. Right. So the inverse relation is actually Fj is the sum on I alpha star Ij Fi prime minus beta Ij F prime star I.
I need to leave now, but I just.
What's that?
I want to just
Say that again?
I have to leave now, but
Oh, you
I just
have to
wanted
go,
point
okay.
out that it's potentially dangerous to use delta and delta, where delta is the.
Yeah, that's bad notation. You're absolutely right. So we've got two delta, this is terrible notation. He's exactly right. There's a simple way out of that, though. What I can do is just replace delta with D. I don't know why I use Greek letters at all. I usually avoid Greek letters, but I guess I have not, this is the first time I worked through this material, so I basically just reached for whatever I could find. So I'll just call them DJL. So that's the Fj in terms of the F prime, and maybe I should write the original one. F prime J is sum I, alpha Ji, Fi plus beta Ji, Fi star. Okay, and if we write the indices down in this order, we see that there's nothing diabolical about the choice of the order of the indices. Ji is quite natural for the expansion of the primed solutions in terms of the unprimed solutions. And these, of course, are called Bogoliubov transformations. That's a V. Okay. Let me get. Let's see. Did anybody ask a question and not get a candy? Austin, didn't you ask a question? I think
Yes, sir.
give you a
I
candy.
think it'd be sure.
All right. Now, let's consider what happens to vacuum states under these conditions. And before we do that, let's recall what we found, namely that AL was equal to FL, the scalar product of FL with phi, and AL prime was the scalar product of F prime L with phi, and a dagger L was minus, well, it's obviously, this is the Hermitian adjoint of that, and so this will be FL phi complex conjugate, and I was about, oh yeah, this actually works great. You can move the star inside at the price of a minus sign, and so this gives us minus FL star, but phi is Hermitian, so the star has no effect. The field phi is Hermitian. So what I'm using is, once again, this unnamed property that Fg star is minus F star G star.
Can I, so that property is bothering me. Is it just
Maybe
like,
let me just do this quickly. So this is hermiticity, and the other one is, so I've copied them correctly, I hope.
I think so.
yeah, is there a, Is this just to put a restriction on what your F and G are, so that, what is it?
It sort of comes from the.
There's a definition of a scalar product. Given the scalar product that has these properties, we have all of this that follows. And you can define, depending on what theory you're dealing with, you can define the scalar product in different ways, but you want to make sure that it's Hermitian and has these other properties. And then we're also assuming that the solutions that we're talking about, the F's, form a complete set, and you can normalize them and so forth.
Well, what I'm looking at is if F and, so this restricts you, so if F and G are real, you can't have that. Right? Because
Yes,
F star is the same as F.
Hmm?
that's
So F
right.
and G
Right.
But there's the I outside of the inner product, so you still get a minus sign. Maybe
Well,
just-
no, I'm just saying it restricts what your possible values
No,
are.
he's right. F and G could be real because the inner product of F with G has an extra I. See, the I's have it.
I don't buy that one yet. You have the I there, but you're gonna have the I there no matter what.
Sure.
Or what I'm saying is F star is equal to F. So you could just rewrite that as FG star is equal to minus FG.
Hmm?
Yeah, right. If F and G are real, then FG star is equal to minus FG. But that means that FG is imaginary.
It's because, yeah, the inner product is the I outside, right?
Inner
So
product,
the
okay.
integral of all this stuff is
Inner
real,
product
but
has
the
the
I
I
outside
outside. Okay.
makes everything imaginary. Yeah.
And then if they're purely imaginary, you'll get something similar.
Yeah, exactly. Yeah, if they're, it's kind of funny, if they're purely imaginary, you get.
Oh, I owe you a candy then.
No, I had Cheetos.
So this is minus FL star phi and A prime L dagger. Well, we can do the same thing. We can take the complex conjugate effectively of that, and so we get a minus sign F prime star L phi, and indeed that's what you get in the direct calculation. Okay, so now, we can ask, well, what's the relationship of these annihilation creation operators to each other? And so in particular, let's look for A prime L. What is this? Maybe I'll go over here. So nice boy. A prime J then is, that's this thing. So that would be Fj prime with the field. But now I'm going to express the field in terms of the unprimed creation and annihilation operators. Actually, well, I could do that, or I could do, all right, let me do it in two steps. The first thing I'm going to do is write the F primes in terms of the F's. So this is actually F prime J is this thing, alphas plus betas. And so this will be alpha Ji Fi plus beta Ji Fi star, comma phi. And so this is in particular sum on I, alpha Ji Fi phi plus beta Ji Fi star phi. And now we've computed what these are. Fi with phi is AI. So this is equal to sum on I alpha ji ai. And now Fi star phi is minus that, but these are not primes, so it's this one. So Fi star phi with a minus sign is minus a dagger. So this is minus beta ji ai dagger. So that's a very interesting result. It tells us that intrinsically the annihilation operators of one system are related, are linear combinations of the annihilation operators and the creation operators of the other system. And consequently, that we're going to get something very funny happening unless the betas are all 0. And the inverse relation is Aj, which is Fj on the field phi, is the sum on I. And now what I'm going to do is I'm going to express the Fj in terms of the alpha stars and the F stars. And, okay, the alpha stars and the F stars. And let me just look at the alphas for a minute. Right, okay. Notice here that this alpha JL is equal to FL F prime J. All right, never mind. I was going to say something, but what's bothering me here is that this star here and no star there and beta here and beta there. It's a little bit puzzling. I hope I've got everything correct here. All right, this is what's in my notes. I could have made a mistake. The notes are on the class web page. Anybody who finds a mistake and tells me about it, of course, gets extra credit. By the way, next week is spring break, right?
Spring break?
Okay. So one thing that I will ask you to tell me about is what you want to hear in the rest of the semester after spring break. In other words, what subjects you prefer me to cover. I could go back and talk more about path integrals because we sort of stopped kind of 2/3 of the way through the chapter. We stopped because we were running out of time, so we just rushed through the rest of the chapter. That's one thing I could do.
Still never did that nonlinear sigma model.
Yeah, and are you interested in the renormalization or in a discussion of the nonlinear sigma model?
Yeah, discussion of the nonlinear sigma model, renormalization, and like deriving effective action for it.
Give me the rest of that. What?
And the effective action for the nonlinear sigma model.
All right.
I'm doing renormalization group thing.
Let's talk about that afterwards.
Okay.
Okay, let's see. So let me get back to the story now. So the annihilation operator is fj with phi, and we can express this as alpha star ij f prime I. So what I'm doing is I'm writing the f's in terms of the f stars. And in fact, let me do this in 2 steps. In the notes, I kind of wrote this in a different way. So we'll write the fj in terms of the f primes. So that's alpha star ij f prime I minus beta ij f prime I star. It's all of that with phi. So that's fj expressed in terms of the prime solutions in a product with phi. And so this is the sum on I, alpha star ij f prime I with phi minus beta ij f prime star I with phi. And these coefficients are, well, these are the formulas for the annihilation operator. The annihilation operator in the prime basis is the inner product of primed f with phi. So this is the sum on I, alpha star ij, ai prime. And then the creation operator is minus f prime star inner product with field. And so here we have minus f prime star with the field. So that's plus beta ij a I prime dagger. And fortunately, that's what it says in the notes. So this again says that the annihilation operators in the first system are a linear combination of the annihilation operators in the second system, but also involve the creation operators in the second system unless all the betas are 0. Now, the vacuum of the first system is defined by the equation that all of the for all modes I, the annihilation operator maps the vacuum vector, vacuum state to 0. And the vacuum state of the second system, the prime system, is defined by an infinite set of equations here. For all I, the annihilation operator of the ith mode of the prime system annihilates the vacuum state of the prime system. So those are the definitions. And the adjoints of these equations are well, let's put it this way. Let's look at this. Let's see, what did I do here? Right, I want to express the A prime in terms of the A's. And, right, okay. So let's write these equations in matrix notation. The top equation is A prime is equal to the matrix alpha times the vector A minus the matrix beta times the vector A dagger. Okay? And the lower equation is the vector A is equal to, and it comes down to here, it's the vector alpha adjoint on the vector A prime plus the vector beta transpose on the vector A prime adjoint. For some reason I didn't write both of those equations down, but I should have. In any event, if we now look at this equation, what this equation is A prime on the, or let us instead consider what the annihilation operators of the first system are on the vacuum state of the prime system. Well, that's this structure here. I think I may have. Ah, yes, okay. So, right, so let's rewrite well, let's just write it down. A is alpha dagger A prime, that's a prime, plus beta transpose A prime dagger on the prime vacuum, and that's a prime, right? So this is, I'm using this equation here. This gives 0, and so this is beta transpose A prime dagger on the prime state. So that means that it's what we said before, namely that the annihilation operator doesn't annihilate the other vacuum unless all the betas are 0. Let me just make sure I've got everything straight here. This is F right, okay. All right, I think this is all right, but I think there's a typo in the notes at some point here. So now what we can do is we can compute, we can take the adjoint of this equation, and the adjoint of this equation looks like this. We'll take the adjoint of this, and what we get is the bra of the prime system vacuum, A prime beta complex conjugate. And so now if we look in the prime vacuum, what is the sum of all the number operators for the unprimed system? Well, in matrix notation, this is, in fact, I could have written it the other way, namely A prime right, A prime beta star, and then this which is beta transpose A prime dagger. So basically, these guys typically do not annihilate the vacuum. In fact, what the A primes do is they map the vacuum state into the one particle state, or one particle of a particular mode. I'm using matrix notation here. And we're summing over, let us say, Ij, Jk, and not Jk, Ji, I, because we're summing over the i's there. And so that's actually a trace. This state we're assuming is normalized, and so this is the trace of, it's the trace of beta star, beta transpose. I think there's no point in talking about it as a trace. Let's just say that it's, it's the sum of the number n prime sub I times beta I star j, beta j I transpose. And this structure is intrinsically positive. This is, in fact, it's the trace of beta transpose adjoint beta transpose is another way of saying it. And that's non-negative, and in fact it's equal to the sum of beta ij absolute value squared summed over all I and j. So the only way that that's zero is, the only way that all of them are zero is that. Equivalently, maybe I should rewrite this in a different way. This is a sum over modes, 0, AI prime, A prime dagger, 0 prime. And this is, normally we'd be quantizing with, these are discrete modes, so this is just 1. So let me just call that as, say that that's 1. And so this is, this is just a sum beta, sum on j, sum on I, and it's actually sum on I and j of beta absolute value, beta ij absolute value squared, because that times that is, we have these i's the same. Right, so basically the upshot is that there are always particles in the second vacuum, or to put it differently, from the point of view of one system, there are always particles in the vacuum of the other system, and from the point of view of the other system, there are always particles in the vacuum of the first system, as long as any of the betas are non-zero. And so whether the betas are non-zero depends upon what two physical systems you're talking about, what the mode functions are, what the inner product is explicitly.
We haven't said anything about wanting to preserve commutation relations. Is that something we want to do?
I'm sorry, say it again?
We haven't said anything about wanting to preserve commutation relations. Should we preserve canonical commutation relations?
Yeah, well, yeah, you see, you came in late.
You said this in the very beginning.
Yeah. What I said was, in fact, the original question was, how is it that we can use the same field throughout the whole lecture? And what I said was that what we mean by a field is just a function of space-time such that its commutator with the with its conjugate momentum is I times a delta function, and the canonical momentum is given by that, and once we have that field, we then expand it in terms of these different, in terms of mode functions. The mode functions have to satisfy the equation of motion of the field, and the equation of motion of the field I forgot to write down. All right, so that's a key thing that I should have written down. The field equation for the scale of field is that this is m squared square root of g. G is the absolute value of the determinant. I forgot to say that also. G is equal to absolute value determinant GIK. And, okay, we want the field to satisfy this equation, so if we expand it in terms of mode functions, we want the mode functions to satisfy the same equation. But one could have different solutions for the field equation, and you could also say, well, let's consider the same field in different coordinate systems, and in different coordinate systems, this field equation would be different and the mode functions would be different. I must say this is confusing when one is talking in terms of space-time. In terms of ordinary quantum mechanics and quantum field theory and Minkowski space, it's pretty clear, well, more or less clear what's going on. But and I wanted to show you a nice example today, but I couldn't actually get through it. What I did was I mean, the thing I wanted to do was to compare an ordinary observer, inertial observer, then an observer in an accelerated reference frame, and show that there's a difference. And well, here we've got Blackboard over here. I can show you what I was thinking about, which is, this is something that was due to Rindler, who was one of a major relativist. He actually only died about a month ago. He was born, I think, in 1924. So he was 95. In any event, it's the ds squared here is dx squared plus dy squared plus dz squared minus dt squared, And in the other coordinates, we have d capital X squared plus d capital Y squared plus d capital Z squared minus capital X squared dt squared. So these are x, y, z, t are the Rindler coordinates for the accelerated frame. And, well, it's easy to see that GIK is minus x squared 1, 1, 1, with zeros everywhere else, and GIK is minus x to the minus 2, 1, 1, 1. But, and one could also write down the field equation, and the field equation then is d by dt of minus x inverse d by dt of f plus, well, it's actually x d2. No, I'm making a mistake here. Hold on. Oh, we don't have a small. This is the x derivative of x, x derivative of f. And then the others are simple. It's capital X d capital Y squared f plus d capital Z squared f is equal to m squared capital. So that's the equation, and one can say, well, f of tx y z is just f of t and x e to the I y py plus I z, well, it's an ordinary p, I z pz. And then one can define capital N squared as little m squared plus py squared plus pz squared. And then the equation simplifies, but it didn't simplify enough for me to be able to solve it. What one has is d by dt squared f plus x inverse partial x of f plus partial 2x f equals capital M squared f. And I don't know, I mean, that's a partial differential equation with two independent variables, and it's nonlinear because of the x outside. I imagine, well, I just don't know if there's a, that's one of the problems of general relativity, by the way. Anytime you actually try to have a real example of anything, you find differential equations that are non-trivial, and if you can't solve them, you're basically stuck. And so, I don't know. One of the pities is that the federal government was supporting a program in symbolic arithmetic or symbolic calculus, symbolic mathematics called Maxima, and they then somehow the project either lost funding or I don't know what happened to the project. It was by far the best program for symbolic mathematics, and instead it was overtaken by Maple, commercially by Maple, which is quasi-commercial, and Mathematica, which is aggressively commercial. And so Anybody who solves the equation gets super extra credit.
Multiply everything by x squared. Can you separate out the t variable or no?
You want to multiply everything by x squared.
And then you can separate
Yeah, and
out
then like
t.
define f as
Well, that
like-
might be a good idea because it makes things a little bit simpler. Then we get minus d2 with t derivative
Isn't there like Photoshop
plus
equation or
x
something that you get?
dxf, but then we have x squared d2xf equals m squared x squared f.
And then
Is
you
that
can
what you wanted to do?
Now you can separate out t.
Separate out t.
Consider first term linear.
Right?
Yeah, this is separable. If you like define f as like chi of x times tau of t.
No,
So you're
it's
saying,
like,
this might be great. So you're saying write f of t and x
yeah, I know, right? It looks like
as
it's a
f of t
F of x.
times some f of x?
Yeah.
Yeah, I think it works then. You divide through by like,
All right, well, let's just see what we maybe should do is call this, in honor of Austin, we'll call this a of x. So this is then minus f double dot a plus, I'm going to use lowercase x's just because I hate capital letters. This is Brindler's notation. A prime plus x squared a double prime
It's not.
is equal
It's
to
not mentioned.
m squared x squared.
If it's x squared is in the.
Oh, I left out the f, right?
It's
Okay, so there's an F here.
It's in the d1. The constant term is
Right.
dy dx squared. But it's
Hmm.
not.
so what do you end up with?
Okay, so this looks pretty good, actually. So we divide through by f, and we then write f as just a harmonic function of t.
Mm-hmm.
Or, I mean, it might be an exponential, anyway, an exponential function of t.
Yeah.
So we have minus f double dot over f plus x a prime plus x
Divided by a.
squared a double prime equals m squared a, m squared x squared a.
And you divide everything by a too, right?
Divide,
Everything should be divided by f times a. That way you cancel the a on the f double dot term.
oh, sorry, you're right. I wanted to get rid of that, yeah.
Yeah. And then you erase that.
Right. So all of this is just a function of x, and all of that is just a function of t. And so we can replace this by something we'll call alpha. So we have alpha plus x a prime over a plus x squared a double prime over a equals m squared x
That's
squared.
Yes.
And that's a hell of a lot simpler.
Like modified pencil.
I don't know, this is what I got.
You actually solved the whole thing?
No,
basically?
this, I'm just,
Basically what?
so this is the function of x. Chi is a function of x.
Yeah, it's a
Tau is a
Bessel.
function
That's a
of t.
goddamn Bessel function. Yeah.
You get this.
The
That's,
the x
I could have got it wrong, but.
Oh, it's okay. There's probably some modified Bessel function or something like that. I don't know. Yeah.
But
Yeah,
essentially
modified
you end up
Bessel
with-
function. That's probably what it is. I think that the solution to this is a modified Bessel function.
Seriously?
Yeah,
It's
yeah,
very
yeah.
close to the Bessel.
It's
Really?
very close to the Bessel equation. I think it might be a modified Bessel function.
Okay, this is terrific, it's fantastic.
Bessel function.
Looks very similar to the Bessel.
Right.
I don't know.
Sure, so
Two
for-
years.
Yeah, it certainly looks like it.
think. I bet.
Well, you guys are, well, there's an extra term, isn't there? Or did I screw up?
No, I think. No, there's the only difference is like a difference in sign here.
There's an overall-
When it's x squared minus alpha squared. It should be like.
But this thing is linear in
But
y.
I think like.
This is linear in y,
It's not.
and, well, this is linear in a after you multiply through.
That's a square. It's not linear.
No, linear in the function.
So you have an a
So linear in the
here,
function y.
Okay.
No, I think you've got an extra x
and an a
squared.
there. Okay, well, this is cool. So this is that modified Bessel function or just a regular Bessel function?
It is indeed a, well, it's almost a modified Bessel equation. It is almost, what, oh heck, yeah, no, if you make alpha negative, if you make it equal to negative n squared.
Yeah, well, I don't know
That
what
is
the sign
indeed-
of alpha is.
If you make it minus n squared, it is indeed a modified Bessel equation.
So you want alpha to be what? Negative?
Like minus n squared. Does that work out with your?
So you want minus f double
Oh, and that
prime?
makes sense, because, right, if f is a harmonic function, alpha.
You want it to be like this?
Oh shit, yeah, that might be a little funky,
Oh,
but I
it's,
guess so.
That's
Yeah.
an exponential, not.
Yeah, it's an exponential, it's not harmonic.
Okay, so then
It's a little funky.
it's a growing function.
Yeah,
But on the other hand, this is a very crazy situation. This is one of constant acceleration. And so the possibility that something really weird is happening. All right, I think you guys did a fantastic job of
very close.
bailing me out of a difficult spot. So let's put it this way. I will try to spruce up the notes a little bit and put them on the class webpage. And if you want to go further with this, that's great. I think we ought to, because this is a nice example of Hawking radiation and this whole idea that an accelerated reference frame gives rise to that you get particles produced. Actually, there's another example of this, now that I think about it, that's completely physical and very simple. You can imagine somebody in an elevator. Now, what was the trick? I think it's somebody in the elevator is holding a charged sphere. Okay. But in fact, this elevator is defective and there's no cable, and so it's actually accelerating downward. And then so some observer looks at the elevator and sees photons because there's a charge that's radiating. On the other hand, in the rest frame of the elevator, the charge is static. There's no, so that's a physical example of what we're talking about. And just goes to show you that anytime Mr. Einstein is involved, things get very surprising very quickly. So I guess we can turn this off, or have you already?
Wait,